Welcome to Module 4, Project Management Techniques. In this module, we'll explore key tools that help us plan, schedule, and control our projects effectively. Project management techniques like Gantt chart, critical path method, CPM, AON and AOA network conventions, critical path analysis, project scheduling. Advantages of CPM. By the end of this module, you'll be able to use a Gantt chart, draw network diagrams, perform forward and backward passes, and determine the critical path for any project. Let's start with the Gantt chart, one of the simplest and most widely used project management tools. A Gantt chart is a visual timeline that shows tasks, their order, and how long each will take. It helps project teams plan activities and track progress over time. For example, when designing a new product, we might first design, then prototype, test, revise, and finally move into production.
So, it helps us track progress and deadlines visually?
Exactly. You can easily see which tasks overlap, which are running late, and what's coming next. It's like a project calendar that keeps everyone on the same page. Gantt charts are especially useful for showing start and end dates, task dependencies, and milestones. Most project management software, like MS Project or Trello, use Gantt-style views to visualize progress. The critical path method helps identify which tasks directly affect your project's finish date. It's a step-by-step process that helps you plan, schedule, and control your project effectively. There are two ways to represent project activities in a network, AON and AOA. In AON, activity on node, activities are shown as boxes or nodes. In AOA, activity on arrow, activities are shown on arrows, and circles represent events.
So AON uses boxes for activities and AOA uses arrows. Easy.
Let's look at a few examples. In the first case, activity A must be completed before B can start, and B must finish before C begins. In AON, this is shown as 3 connected nodes, A, B, C. In AOA, it's shown with arrows labeled A, B, and C connecting the sequence of events. Both diagrams express the same logic, that one activity follows another. Now, suppose activities A and B must both be completed before activity C can begin. In the AON diagram, both A and B connect into node C. In the AOA diagram, arrows for A and B converge at a common node before activity C starts. This shows that C has 2 predecessors, meaning it cannot start until both A and B are finished. Sometimes, a project requires an activity to show a dependency relationship without any actual work. In such cases, a dummy activity is introduced in the AOA network. For example, if activity D depends on both A and B, but activity C only depends on A dashed arrow is added as a dummy activity to keep the logic correct. Dummy activities have 0 duration but are essential for showing accurate dependencies in AOA diagrams. To perform critical path analysis, we calculate 4 key values for each activity. ES, earliest start. EF, earliest finish. LS, latest start. LF, latest finish. ES and EF tell us when an activity can start and finish. LS and LF tell us when it must start and finish without delaying the project. Here, we calculate the earliest start and earliest finish times as we move forward through the project network. The longest continuous path through all activities is known as the critical path. It shows the shortest possible time in which the project can be completed.
In this session, we'll perform a critical path analysis for the Milwaukee paper manufacturing project. Our goal is to identify the critical activities, calculate early and late start and finish times, and determine the total project duration. Let's begin by reviewing the project's activities, their dependencies, and duration in weeks. Activity A, build internal components, 2 weeks. Activity B, modify roof and floor, 3 weeks. Activity C, construct collection stack, follows A, 2 weeks. Activity D, pour concrete and install frame, follows A and B for weeks. Activity E, build high-temperature burner, follows C for weeks. Activity F, Install pollution control system, follows C, 3 weeks. Activity G. Install air pollution device, follows D and E, 5 weeks. Activity H, inspect and test, follows F and G, 2 weeks. These tasks together form our project network.
Let's calculate forward pass for Milwaukee paper manufacturing project. Now begin with the forward pass to calculate the earliest start, that is, ES, and the earliest finish, that is, EF, for each activity. We'll move through the project network step by step. Activity A starts at time 0 because it's the first task in the project. The duration is 2 weeks. So we calculate EF by adding ES plus duration. That's 0 plus 2 equals 2. Therefore, the earliest finish for Activity A is 2 weeks. Activity B also starts at 0 weeks. The duration is 3 weeks. We add 0 plus 3 equals 3. So the earliest finish for Activity B is 3 weeks. Activity C can only start after Activity A is completed. Since A finishes at 2 weeks, ES for C is 2. The duration of C is 2 weeks. We add 2 plus 2 equals 4. So the earliest finish for Activity C is 4 weeks.
Activity D. Activity D depends on both A and B being completed. We take the later finish time of the two. A finishes at 2 weeks, B finishes at 3 weeks. So ES for D is 3. The duration is 4 weeks. We add 3 plus 4 equals 7. So the earliest finish for Activity D is 7 weeks. Activity E. Activity E can start only after Activity C is done. C finishes at 4 weeks, so ES for E is 4. Duration is 4 weeks. Add 4 plus 4 equals 8. Therefore, the earliest finish for E is 8 weeks. Activity F. Activity F also follows C. ES for F is 4 weeks. The duration is 3 weeks. Add 4 plus 3 equals 7, so the earliest finish for F is 7 weeks. Activity G depends on both D and E. D finishes at 7 weeks, and E finishes at 8 weeks. We take the later one, that's 8. So ES for G is 8. Duration is 5 weeks. Add 8 plus 5 equals 13. Therefore, the earliest finish for G is 13 weeks. Finally, Activity H depends on F and G. F finishes at 7 weeks, and G finishes at 13. We take the later finish time, that's 13. So ES for H is 13. Duration is 2 weeks. Add 13 plus 2 equals 15. So the earliest finish for H is 15 weeks. The earliest finish of the final Activity H shows the total project duration. Therefore, the Milwaukee paper manufacturing project will take 15 weeks to complete if everything runs on schedule.
Now, A, C, E, G, and H together, they form the sequence ACEGH. This is the longest path through the network, with a total duration of 15 weeks. Any delay in these activities will delay the entire project. So critical path is based on time relationships and dependencies, meaning which activities depend on which others and how long they take. Why the critical path matters? The critical path method is one of the most powerful project management tools. It helps you identify key tasks that directly affect project completion, allocate resources efficiently, monitor progress and anticipate delays, keep the project on schedule and within budget. And that's the last, but not the least, the summary of the forward pass, calculating earliest start, ES, and earliest finish, EF. I hope this session helped you clearly understand how each activity connects and how to calculate ES and EF step by step. Remember, mastering the forward pass is the foundation for understanding the backward pass and finding the critical path in project management. Thank you for watching, and keep learning.